Hello everyone, welcome to the video lecture series of Basic Electrical Engineering Lab. Today we will be discussing our experiment number 7. So the aim of today's experiment is to find out the meter constant of a single phase energy meter. Now let us see what is this single phase energy meter all about. So basically one important difference to be noted here is that all the previous experiments were your breadboard based experiment wherein you were provided with a circuit diagram and you were required to make the same circuit onto the breadboard, whereas in this experiment we are provided with a separate fully equipped panel of single phase energy meter to study the aim of our experiment successfully. Let us now move on to the theoretical aspects of our experiment. So energy meter is basically an integrating type instrument which is used to record the energy consumed by the load during a given period of time. So basically, in other words, I can say that energy meter is an electrical instrument that measures the amount of electricity consumed by the consumers. And how do the state electricity department gets to know that how much energy you have utilized? So basically the state energy department, what it does is, or your state regulatory services, what they do is they install these instruments at every places like home, industries, organization to charge for the electricity consumption. Fine. So the energy meter available with us in the lab has the following parameters. Okay, we'll come to that later on. But one striking term here which we have noticed is integrating instrument. It is clearly mentioned that energy meter is an integrating instrument. Now the question arises as to what is an integrating type instrument. So if we look at our vast categorization of types of instrument, we'll see that our integrating instruments lie somewhere here. All right, so to understand the theory about integrating instrument, let us first check out our basic two classification of electrical instruments. All right, so our electrical instruments can be classified into two broad categories, which is absolute instruments and secondary instrument. So basically absolute instruments are those instruments which give the value of quantity to be measured in terms of deflection of pointer as well as some constant of the meter, whereas secondary instruments directly give the value of quantity to be measured in terms of deflection of pointer, which moves on a calibrated scale. So obviously in case of absolute instrument, some mathematical calculation is required for knowing the value of physical constant, whereas in case of secondary instrument there is no mathematical calculation required for knowing the value. The output of this type of device can directly be obtained, but one problem with them is a calibration of these instruments with standard instrument is essential for the measurement. So basically in our day-to-day life we always use, in case of laboratories, in case of industry, we always use secondary instruments. All right, so the example of absolute instrument can be your tangent galvanometer, and example of your secondary instruments can be your general ammeters, voltmeters, watt meters, which you see in your labs. Now moving further, the difference between analog and digital can be easily found out. Now let us move further again towards deflecting type instrument and null deflection type instrument. So basically deflecting type instrument, what happens is in this instrument the value of measuring quantity is determined through the deflection of pointer, as simple as that, as the name suggests. But in case of null detection, what happens is the zero or null detection, yeah, or you can say deflection, indicates the magnitude of measured quantity. So in null deflection instrument, there is one known quantity and there is one unknown quantity. When the value of known quantity and unknown quantity are equal, the pointer shows zero deflection and we can easily find out our given, or you can say desired value of measuring quantity. So moving further, we see three more classification, which is your indicating type instrument, your integrated type instrument in which we are interested, and your recording type instrument. Let us cover them one by one. Basically, in case of indicating type instrument, what happens is as soon as you complete the circuit, the deflection of pointer indicates the value of quantity to be measured. All right. And what happens is the scale of the indicating instrument is already calibrated in terms of the unit of quantity to be measured. Meaning, for example, if this is a voltmeter and it is measuring voltage, the scale of your voltmeter will already be calibrated in terms of what? In terms of volts. All right. Now let us understand what are recording type instrument. The instrument which records the circuit condition at a particular interval of time is known as your recording instrument. So basically what happens here is the moving system of the recording instrument carries a pen which lightly touches a paper sheet, and the movement of the coil is traced on the paper sheet. So the curve drawn on the paper shows the variation of the measured quantity over a certified duration of time. All right. So now let us come to our main classification in which we were interested, which is your integrating type instrument. So integrating instruments are those which measure and register with the help of a set of dials and a pointer the total amount of electrical energy supplied to a circuit in a given time. All right. So this is the definition of integrating instrument, and its example is your energy meter, and it is also being called as your watt hour meter. Okay, so let us understand why it is called a watt hour meter. So you already know that the basic unit of power is what? It is watt, and it is being measured with the help of a watt meter. And 1000 watts make 1 kilowatt. So I can say that if one uses 1 kilowatt hour in 1 hour duration, I will say that 1 unit of energy is getting consumed, or you can say 1 kilowatt hour of energy is being consumed. Let me give you one more example. For example, if there is a motor of 2 kilowatt and it is being operated for, let us say, 5 hours. So how much energy will it consume? How much electrical energy? It will consume 10 kilowatt hour of electrical energy. And if I talk about a standard, I will say if 1 kilowatt is being used in 1 hour duration, you will say that 1 unit of energy gets consumed. So this unit of energy is the same unit for which you are charged by the electricity authority. So it would be very interesting if you could find out that what is the price of 1 unit of electricity in your state. Okay, this I'm assigning you this task, which is to find out that what is the cost of per unit of electricity in your particular state. So moving on further, so I can say that energy meters measure the rapid voltage and currents, calculate their products, and give what? Give us the instantaneous power. And when this power is being integrated over a time interval, I will say that it gives us the energy utilized over that time period. I hope that you are clear with integrating. So this is how your actual energy meter looks like, and this is its internal circuit diagram. So if we talk about the classification of energy meter, we are basically having two types of energy meter, which are electromechanical type, and second one is your electronic type. So electronic types are most common these days, but for our experimental purpose and to understand the working of energy meter to its full level, we are going to study what we are going to study electromechanical type in our lab. So why? Because it is basically a well-known and most common type of age-old energy meter. It basically comprises of a rotating aluminum disc, as you can see here, as well as in the internal circuit diagram, which is being placed on a spindle between the two electromagnets. These are the two electromagnets. This is your shunt and this is your series magnet. So basically what happens is there are eddy currents which are being induced in the aluminum disc when it cuts the flux produced by these two magnets, and as a result of interaction of eddy currents and magnetic fields, a deflecting torque is produced in the disc, and the disc slowly starts to rotate, and the speed of the disc is directly proportional to the amount of power which is being consumed. Meaning, if your load is higher, the disc will start to rotate at a much more higher speed, and as soon as the disc starts to rotate, what happens is this dial which is present here also starts to move and gives us the value of electrical energy which is being consumed. Fine. And for stopping this disc, there is a braking magnet, which is a type of permanent magnet. So basically we can say that there are four essential components in an energy meter, which are your driving system, your moving system, your braking system, and your registering system, which gives us the value of electrical energy consumed. All right. Moving on to the apparatus required, we'll be requiring a voltmeter, an ammeter, and some resistive load. So in this case, we'll be utilizing bulbs of 100 watts and 200 watts as load. Meaning, as soon as we switch on these bulbs, what would happen is that the aluminum disc would start to rotate, and obviously we'll be requiring a single phase energy meter, okay, which has these ratings already engraved on it by the manufacturers. Now let us come to the formula which will be utilized. So our aim was to calculate the energy meter constant of our single phase energy meter, and which is being given by number of revolutions made by that disk during that time interval. What is the time interval? The time interval is the time duration for which we have turned on the load and divided by the energy consumed by that load. And this energy will also be consumed in that specific time period only. So basically what it denotes is, it denotes that how many revolutions does our energy meter takes to consume 1 kilowatt hour of energy. All right. So, as I've mentioned in previous slide, the manufacturer has already given us a value which is 600 revolutions per kilowatt hour. Now the question arises, if the manufacturer has already given us the value of energy meter constant, why are we calculating it again? So we are calculating it to verify whether the actual value of the energy meter constant is 600 or is it somewhat different from the prescribed value. So moving on to the circuit diagram, let me tell you once again, this is not the diagram of energy meter but the connection diagram which we'll be utilizing on our panel, or you can say in what manner our various components are being connected to perform the experiment. So this here you can see our energy meter which has its current coil and its potential coil connected in this manner. This is our load. In our case we are using various types of bulbs, and this is our single phase AC supply. If it was a three-phase energy meter, we would have used a three-phase AC supply. And these are your general ammeters and voltmeter connected in series and in parallel respectively to calculate the amount of current and voltages. So let us now come to the procedure, or you can say what are the steps that we are going to follow in order to find out the energy meter constant of our single phase energy meter. Okay, so the first point, or you can say the first step, is noting down the initial energy meter reading. As I have already shown you in the diagram that energy meter comprises of a dial which keeps on moving, and the reading from this dial shows us as to how much energy we have consumed. So this dial does not resets to 0, meaning once you have operated, once you have turned on your load, this dial must have moved to a specific value. So if this has moved to a specific value, how will you find out that how much energy you have consumed? So for that you will be requiring two values. First one is your initial values and second one is your final value. Okay, and after separating these two values, we'll be able to find out as to how much energy our load has consumed during that given period of time. All right, now the second step would be to switch on the lamp load. Obviously we'll turn on the lamp load. If we do not turn on our lamp load, what would happen is our aluminum disc will not rotate and consequently our dial would not move further. So in third step, we need to count the revolution made by that disk. So you'll need to carefully count the revolution of disk. The disk has a red marker. If it passes you once, it means that disk has completed one rotation. So we'll count at approximately 25 revolutions of this energy meter disk. And lastly, what you are going to do is you are going to switch off the lamp load and note down the final reading of the energy meter. So let us now check out the observation table of this experiment, and we'll be able to know that what are the various parameters that we need to jot down in this experiment. So the first column in the observation table, as discussed before also, is the most important parameter, which is meter reading before switching on the load, which is denoted by your KWH1. So as I have already discussed earlier, without noting down the initial value, you won't be able to tell as to how much energy has been consumed by your load, right? So after switching on the load, you are going to note down your KWH2, which is the meter reading after switching off load. And the third column in this category is your number of revolutions made by the disk. All right. So let me repeat it once again for you. First one here is your kWh1. For example, whenever you go to your energy meter panel, you are going to check out the dial onto the energy meter and check what is the reading shown to you by the energy meter, and you are going to write it down as whatever the reading is. You are going to write it down like this, and then what you are going to do is you are going to turn on your load and observe that the disk has rotated for 25 rotations. All right, and after that what you are going to do is you are going to switch off your load and you are going to check the final reading of the energy meter by its dial. For example, the final energy reading is somewhat like this, and in the third column you are going to mention as to how much rotation has your disk made. All right, and your fourth column here is the energy consumed by your load. Now the question arises, how will you calculate the energy consumed by your load? So energy consumed can be easily calculated by evaluating the difference between kWh1 and kWh2. So what you are going to do is subtract this reading from your kWh2 and you are going to get as to how much kilowatt hour of energy you have consumed during that time. Now, next column is what? Next column is your practical value of your energy meter constant, meaning the value obtained by the formula, or you can say the value obtained after taking the reading, which is given by the formula N divided by energy consumed. And we all have calculated the energy consumed in the previous step, so I can write it down somewhat like this: N divided by kWh1 minus kWh2. This is basically the difference between these two quantities. What you are going to do is you are going to subtract smaller quantity from the bigger quantity. Okay, so in this manner you are going to get your practical value of the energy meter, and in the last column you are going to find out the error between the practical value and the value which has been expressed or which has been given to you by the manufacturer of this energy meter. So what you are going to do is you are going to find out the error with the help of formula meter constant minus the practical value divided by meter constant into 100. So in this manner you are going to get what? Your difference between the value supplied by the manufacturer and the value which you have obtained from the experimental procedure. So in this manner you are going to say that energy meter, my energy meter constant is this which you have calculated, and in the process of calculating energy meter constant you have also studied how to evaluate the energy consumed in this experiment by a given amount.
So this is how the panel for your energy meter looks like. This here is your actual energy meter whose energy meter constant we'll be finding out. Here you can see your volt analog voltmeter, and on the right side you can see the ammeter for measurement of current. As far as the load is considered, bulb number B1 to B10 are used as load, which are operated by switches S1 to S10. Alright, and this here is your additional DPIC switch which will be used for turning on and off the panel. So if I turn this main DPIC switch on, you will see that all the bulbs will start glowing and a dial here would start to rotate depending upon the rotation of the disc. So these bulbs here can be operated with the help of these switches depending upon as to how much load you want for your. So the first step here is to find out kWh1, which you already know is the initial reading of the energy meter, which would be written under first column. So let us now check as to how to find out kWh1, meaning as to find out how to find out the initial energy meter reading. So by initial reading, I mean the reading of the energy meter before turning on our load, meaning we have not turned on our light bulbs yet and we need to find out as to what is the initial reading of this energy meter. Only then we'll be able to evaluate what is the energy consumed by these bulbs. And how will we do that? We'll do that by subtracting both the readings, meaning we'll subtract final reading and the initial reading, meaning kWh2 minus kWh1. So now let us see how to take the initial reading. Here you can see 5 different divisions. First one here is 1000 division, second one here is 100th division, third here is 10th division, and this is unit division, and this is 1/10th division, meaning if this particular row has 10 subdivisions in it. Alright, so the first 3 divisions you can read very easily, which are 515. Now how to read this fourth value, meaning that your last dial has division, subdivision somewhat like this. If this is 1 and this is 2, then it has 10 subdivisions in between. So this will be your middle point of these divisions, and you can count depending upon where your red marker is aligned. So if you see here, you can clearly see that the red indicator here is aligned with the 9th division between 1 and 2. So let me show you. So your red marker is somewhere here at the 9th division. Alright, so meaning our initial reading is 515, which was easily found out, and for the last dial it would be 19. Alright, so if this red indicator was here, then we would have said that the reading is 515.15. Alright, so let us now jot down our initial reading, which is 515.19 kilowatt hour. Okay, so the next step here is to find out kWh2. And for finding out kWh2, we need to turn on our load, because the kWh2 here is the meter reading after switching off the load. For kWh2, let us now turn on our load, and as soon as we turn on our load, you can see here your aluminum disc starts to rotate, and you'll have to keep in mind that we'll take the reading after the disc has rotated 25 times. So whenever this red portion of the disc crosses you, it means that it has completed one revolution. So in the same manner, you will count 25 revolutions of this disc, and after that you will see that the reading has shifted from your initial reading of 515.19 to a different value. So we have turned off our load, and we can clearly see here that our meter reading has changed. Alright, so let us now find out what is the value of kWh2. Here you can see that 515 has remained same because we have not turned it on for a longer duration. So there is just a slight difference in the reading. But now the red marker here is not between 1 and 2. It is now between 2 and 3. And to be more precise, I can say that the red marker is corresponding to the third division here between 2 and 3. Meaning that your red marker is somewhat here. Okay. So what we are going to do? We are going to write down our final reading, which is kWh2, which would be 515.23 kilowatt hour. Alright, so our next column here is N, which is number of revolution taken by the disk during that duration of time, which is 25. Alright, so how do we calculate energy consumed? Energy consumed can be easily calculated by the formula kWh2 minus kWh1, which is 515.23 minus 515.19, which would give you approximately 0.04 kilowatt hour of energy. So our main aim here was not to find out the energy consumed. Our main aim here was to find out the value of energy meter constant. So let us find it out here, which could be given by the formula N, or you can say energy meter constant can be represented by any value k, let us say k, which would be number of revolutions divided by energy consumed. So number of revolutions here is 25 and the energy consumed here is 0.04. Alright, so which would give us approximately 625. Alright, so the value of the practical value of energy meter constant here is 625 revolutions per kilowatt hour. Alright, but the prescribed value by the manufacturer of this energy meter is 600 revolutions per kilowatt hour. So you can now easily find out the error, or you can say percentage error, between your practical or calculated value and the original value which was prescribed by the manufacturer.